In this video, we'll be going through an entire dependent t-test, going through the process step by step in order to do that hypothesis testing procedure for this situation, including talking about in what situations we use the dependent t-test, all the way through how to report those results. There are three different kinds of t-tests, but for the purposes of this video, we'll be focusing on the dependent means t-test, or the t-test for dependent means, the dependent t-test, paired t-test. There's a lot of different names for this particular test, but I'll be referring to it as the dependent means t-test or the dependent t-test. Specifically, whenever we look at a test, we want to know when do we use this test. And there's a specific circumstance, like all tests, for when we use the dependent means t-test. Specifically, because it's a t-test, we're going to use it when our population variance is unknown. And for the dependent t-test, we also have the situation where our population mean is also unknown. And so our population variance and population mean are both unknown. And in addition to this, for the dependent t-test, we have two scores for each person in our sample that we create a different score with. And usually this takes the shape of a situation where we have a score before a particular event, like our experimental manipulation, medicine, or therapy that we've given to people. And we also have a score for after. Because this is our hypothesis testing procedure, we have our normal 5 steps of hypothesis testing. And so we're going to start out by restating the question as a research and null hypothesis about populations. For this example, we want to see if a breathing technique will lower test anxiety. And so we measure students' test anxiety during a math test, and then we teach them this breathing technique. And after 3 weeks of practicing that technique, the students take a very similar math test during which we measure test anxiety again. And here we have our scores for both before and after they learned that technique. So who are our populations here? Firstly, we have the students who receive training in our breathing technique, our sample. And we also have our comparison distribution, or students whose test anxiety does not change after learning our breathing technique. And so essentially we're comparing these students against themselves, essentially. We're comparing them in the situation where they have had this breathing technique and before they had this breathing technique. If there is no effect of our manipulation, if we assume that the null hypothesis is correct and we think about what that comparison distribution would look like. If the null hypothesis is true, it means that there's no change. Our breathing technique had no effect. It didn't change anxiety scores. And so that means that our difference score would be 0. So our null hypothesis here would be that students who receive training in our breathing technique will have the same test anxiety scores before and after the breathing technique training, or students who receive training in the breathing technique will not have lower test anxiety after learning this. But our research hypothesis is going to be that students who receive this training in our breathing technique will have lower test anxiety scores after learning this. And so we have our research hypothesis and our null hypothesis. When we're using these different scores, we're talking about this kind of repeated measures design. Is how we talk about this, where each person is tested more than once on the same measure. And for each person in this case, we're going to subtract one score from the other. And specifically, we're going to subtract the before score from the after score. So we want to make sure that we have those in the correct order, or it's going to wind up changing our sign, and we don't want to do that. And again, with this kind of t-test, we might call this a paired sample t-test, a t-test for correlated means, a t-test for matched samples or matched pairs. And all of these names are different names you might hear when we're using this kind of different scores where we have a before and an after. And these are all variations on the theme of what we're calling a dependent t-test, just different names for the same thing here. And essentially, once we get these different scores, the important part is that once we get this different score, we have before and after scores, we do this subtraction, and then we treat the rest of our analysis as though this was a single list of scores. And so those different scores are the only scores that we're going to use once we calculate them. And so we have our scores here for before and after these students learned this breathing technique. We're going to do that after minus before different score calculation. And we can see that here. So we're going to take our after score, subtract our before score. I like to rewrite these here. And we have those answers there. We can subtract those out. Once we've done that, we want to make sure that we determine the characteristics of our comparison distribution and take care of that step 2 of our hypothesis testing. Step 2 is one of the steps that is going to change in our t-test from what we know perhaps already about our z-test, and particularly steps 2, 3, and 4 we're going to pay special attention to, because while these steps will stay the same in that we'll do these steps in some form, how we do those steps is going to change. And so focusing in here on step 2, we want to always, again, keep in mind what is our comparison distribution. And for the t-test for dependent means, that's the distribution of means of different scores. And again, we want to remember that for our comparison distribution, the important thing about our comparison distribution is always going to be that our comparison distribution has to match our sample. We have to have these things to be equivalent. We have to basically compare apples to apples here. And so because we have different scores, we've calculated different scores, and that's what we're using in our sample to run this analysis, our comparison distribution also has to be different scores. And again, because we have more than one person in our sample, which is typically the case, this is still a distribution of means, and we talked about what that meant in an earlier video. And so here we have a distribution of means, but those means are means of different scores. So we said that for the t-test for dependent means, our population variance and population mean is unknown, but we know that this is some of the information that we typically need when we're getting the information about our comparison distribution. Typically, we need the mean and the variance. And because we don't know these, we're actually going to estimate that population variance based on our sample variance. And so that's how we're going to get around the variance issue. For our population mean, we're going to assume that the population mean is 0. And again, this is because we assume that it's 0 because if the mean of our different scores is 0, it's going to mean that on average, there's no change in the scores. And the comparison distribution is essentially, we're comparing to the case where we imagine that this null hypothesis is correct. There is no difference between our scores, and that's what would make that population mean 0. When we talk about this estimate of the population variance, our estimate, if we use the same formula as our sample, this would be a biased estimate. It'll usually be smaller. The variance for our sample will typically be smaller than population variance or underestimate that population variance. And specifically, this is why we need to adjust that sample variance formula to use this formula for the estimated population variance, as we talked about in an earlier video. And so using that estimated population variance formula is really key here to make sure that we have an unbiased estimate, a really good, strong estimate for our population variance. And so how do we determine the characteristics of our distribution of means? And so this is the information that we had when we were talking about our z-scores, and we can see that these, when we're using our estimated population variance, we have some new symbols here. We have this S squared here. That's going to be our new estimated population variance, and S, which will be our estimated population standard deviation. But these formulas still look pretty similar. So what we're doing here is still going to be much the same. We see that dividing by n, dividing the variance by n, getting the square root of that. And so this is going to be very, very similar to the processes that we used for the z-test. We're just going to be trading out some of these symbols and getting this estimate instead of knowing our actual variance to start with. And so here we'll walk through these formulas, and we'll also note that our shape here is going to be a t-distribution with n-1 degrees of freedom. And so we'll walk through that as well. We'll have to calculate what that shape is based on that degrees of freedom formula. And so We have some, again, step-by-step instructions. Again, each step of these processes is usually fairly straightforward. The key here is really just putting it all together and making sure that you're not missing any steps. So for determining the characteristics of our distribution of means of difference scores for the dependent t-test, first we want to make sure that we've made each person's 2 scores into a different score if we hadn't already. We want to calculate the mean of that sample of different scores that we calculated. We're going to use that mean to calculate the estimated population variance using those different scores. And then we're going to assume that the mean of our distribution of means is going to be, means of different scores is going to be 0. Then calculate the standard deviation of the distribution of means of different scores, and then determine our shape. And so let's walk through what this would look like. So we have our different scores here. I've calculated the mean, and so we know to calculate that mean, we're just going to add these all up, divide by the number of scores that we have. And so then we're going to start working on getting that estimated population variance. And in order to do that, we're going to go back to our formula for that. But we know that the first thing that we're going to do is we're going to subtract the mean from each of our different scores. And so we have that here. Then we're going to square each of those differences, those deviation scores that we've calculated. And so this is these are our answers once we square that. And we're going to add up to get our sum of squares, our sum of squared deviation scores. And then finally, the key here and what makes this that estimated population variance rather than our sample variance is that we're going to divide by n minus 1. And so we have 10 scores here. So we're going to divide by 10 minus 1 or 9. And here we get 7.61. And so this is going to be our S squared. This is our estimated population variance. And so now we have our different scores, we have our mean, we have our estimated population variance. We can assume that the mean of our distribution of means of different scores is 0. And now we have to calculate the standard deviation of the distribution of means of different scores. And so in order to do that, we know that our estimated population variance is 7.61. And I can just plug this in to these formulas essentially. And so we have our estimated population variance, and we need the estimated, the standard deviation of the distribution of means of different scores. And so this is really the number that we need down here just to get the standard deviation. So I can plug in that S squared, 7.61 here, divide by 10 and get which is n, how many scores that I have, how many different scores or how many participants that I have, and get that square root. And so if I do this here, have our variance first as well. And if I do this, I get 0.76, get the square root, and we get 0.87. For our shape, we have a t-distribution with n minus 1 degrees of freedom. We know that that's going to be 10 minus 1 because we have 10 participants here. And so that's going to be a t-distribution with 9 degrees of freedom. And this now is everything we had to do in order to get those characteristics of our distribution of means of different scores. And so now step 3, we have our characteristics. We had to do some extra calculating that we didn't have to do in our earlier z-tests, but that's okay. And just step by step, and now we're back to our main hypothesis testing steps, and we're on step 3 here. And so we've mentioned that we're going to be using a t-distribution and therefore our t-table in order to find our cutoff scores. And we're going to use this a little bit differently than when we used our z-table. And so in order to use the t-table, we first have to determine whether we have a 1 or a 2-tailed test, just like we did when we talked about our z-tests. We want to decide which significance level we'll use. Specifically for our tables here that we'll refer to, we have the option of 0.1, 0.05, or 0.01, and we're limited in this case on these tables to those 3, although obviously any kind of statistical software is also going to be able to give you a very specific p-value. But for our cutoff scores for our tables, we're limited to these 3. We're going to find the column for our significance level. And so if I want a significance level of 0.05, we're going to use that. Make sure you're seeing the top here with these labels. So if I have a one-tailed test and I have 0.05 is my significance level, then I'm going to go down the row for 0.05 until I find the appropriate degrees of freedom. And so let's say I had 0.05, let's say I have 5 people in my sample, 4 degrees of freedom for a one-tailed test. Then I have 2.132 or 2.13 if I round it would be my cutoff score. And so that's how we're going to be using these tables. And so for this particular example, we haven't talked about whether we have a one-tailed or a two-tailed test here, but we know that in this particular case, we are looking to see if this test anxiety is reduced. And so we pay attention to those keywords. And so reduce is something that we're predicting a particular direction. And so we're going to say that that is a one-tailed test. We're not just predicting that they'll be different, we're predicting that there'll be less anxiety. Our significance level here, we'll use 5%, that conventional statistical significance level. And we said that we had 9 degrees of freedom. So one-tailed test, 0.05 significance level. If I go down to 9 here, 9 degrees of freedom, we'll see that this is 1.833. And remember that we're looking for less, and so that's going to be a negative 1.833 or negative 1.83 if we round it. And again, for two-tailed tests, we'll use these 3 columns over here, but we do have a one-tailed test in this case. If at a certain point, so we can see that these degrees of freedom also go up incrementally, 1, 2, 3, 4, etc. At a certain point, it does start to jump and doesn't have all the possible values. So if our study has degrees of freedom that are between 2 values on the table, we'll use the degrees of freedom that is nearest but less than the degrees of freedom in our study. But in this case, we don't have to worry about that. Step 4, we're going to determine our sample score on the comparison distribution, and in this case, we'll be determining our t-score. And so here we have our new formula, our formula for calculating the t-test for dependent means. And what we're going to do here is we have our sample mean minus our population mean and all over our comparison distribution standard deviation here. And so we have this information. We have calculated our sample mean already in step 2. In step 2, we assumed that our population mean is going to be 0. And we have our standard deviation of our comparison distribution as well that we calculated also in step 2. And so now I'm just going to plug in these numbers. So we have negative 2.5 minus 0 all over 0.87, which gives us negative 2.5 over 0.87. Which gives us negative 2.87. And so this is going to be our sample score as we move into making our decision whether we should reject the null hypothesis. And so how do we decide? We're going to decide our final decision of whether we reject or fail to reject the null hypothesis the same way that we did in the z-test. And this is one of those steps that's always going to be the same. And so I like to draw these out because it's, I think, helpful to see this visually. And so I can create a number line like this. I can say, okay, well, our cutoff score we said was negative 1.83. My sample t-score here was negative 2.87. And so I can graph these both. And I can say that my sample t-score here is more extreme. It's further out into the tail than the cutoff score, and so I can reject my null hypothesis. And that's this process for completing a dependent t-test, particularly when we talk about reporting t-test results and how t-test results will appear in research articles. Generally, these follow the following format. And so we might see something like this, where T gives us the indication that this is a t-test. The 24 here is our degrees of freedom. And so whatever is in that parentheses next to the T is the degrees of freedom for a dependent t-test. We have our t-score, our sample t-score. and then our p-value or significance level. And so if we're using our software, typically we'll be able to give an exact p-value. An APA format right now, at least, encourages us to give exact values and use that equal sign when we can. For our purposes, for doing these by hand, the best we can really say is whether it's less than whatever significance level we used, which in this case was 0.05. And that concludes our process of using this and interpreting and writing up this dependent t-test here.